Next, we will see the extraction of crude metal, that is impure metal, because the ore may contain other minerals and again earthy impurities. So this will also get reduced during extraction of the metal. So they will form as impurity. Silicon dioxide may be reduced to silicon, and that may be present as impurity in the metal forms. Now other minerals may get reduced. So the metal of the mineral may get involved in the main metal to be produced as impurity. So we get an impure metal, and impure metal is called crude metal. Usually sulfide ores are oxidized to the oxide ore. I consider a sulfide ore, that is zinc sulfide, and a reducing agent, that is carbon. Now carbon will combine with sulfur, forming carbon disulfide, and 2Z, and such an equation is possible. Now zinc oxide may also get reduced using carbon, and zinc and carbon monoxide are formed. Now here, when the sulfide ore is reduced using carbon, we get carbon disulfide, which is a liquid. Whereas when the oxide ore is reduced, we get carbon monoxide, which is a gas. Now a gas is having a higher entropy, a higher randomness of molecules than a liquid, so that the entropy change for this reaction is higher than the entropy change for this reaction. For both these reactions, entropy increases during the forward reaction, because in a liquid the molecules are more free to move than in a solid, and in a gas the molecules are much more free to move in a random manner. So entropy is very high when a gas is formed as the product. So there is a positive entropy change, and according to the equation delta F, or we can call it delta G, both delta F and delta G denote the same thing. Delta G or delta F is equal to delta H minus T delta S. In this equation, if delta S is positive, then there is naturally the tendency for delta G to be negative, and if delta S is more positive, then the tendency for delta G to become more negative is there. And so a gaseous product formed during the reaction will favor a much higher negative value of free energy, and when free energy is negative, the reaction is spontaneous, so that a sulfide ore is converted to oxide ore before reduction. Now for extraction of crude metal, two processes are first involved before the actual reduction process. Now one process is called calcination, CALCINATION. Now calcination is heating the ore, concentrated ore, in the absence of air in a furnace. Now there the volatile impurities are driven away, and if the ore contains a carbonate, then the carbonate decomposes to carbon dioxide and the oxide of the metal. So calcination means heating the ore mainly in the absence of air. And roasting, the difference between calcination and roasting is that roasting occurs in presence of air. So it is an oxidation process. So during calcination, volatile impurities or volatile compounds, here Fe2O3 water is volatile, and at high temperature water vapor is given away, leaving behind Fe2O3, and zinc carbonate decomposes to zinc oxide and carbon dioxide gas, and this gas is given out. So we get the oxide of the metal. Now roasting involves heating the ore at high temperature in a furnace with a supply of air. Now sulfide ores, when roasted, we get the corresponding oxide ore, oxide of the compound, metal, oxide of the metal, and sulfur dioxide gas. Now consider again the equation delta G is equal to delta H minus delta S. Now there is a particular type of graph called Ellingham diagram. Now there standard free energy change is plotted against the temperature. Now for the reaction 2C plus O2 giving 2CO. Now carbon monoxide is a reducing agent. The corresponding standard free energy change delta G0 is roughly 5,000 kilojoules per mole, and for oxidation of iron to ferrous oxide at 1600 degrees Celsius, the corresponding free energy, standard free energy change is nearly minus 200. Here it is minus 500. Now Ellingham diagram is a plot of temperature against standard free energy change for various reactions, and we see from this figure that as temperature changes, the standard free energy also changes because of the equation delta G 0 is equal to delta H0 minus T delta S. Standard entropy change maybe denoted as delta 0. Anyway, this is an equilibrium value, the standard free energy change at equilibrium. Now whatever be the nature, is Ellingham diagram gives us an idea regarding the change in free energy with the temperature. So delta G with the T, that is this graph, and the standard value represents a value at the standard temperature and standard pressure, and standard temperature is usually 25 degrees Celsius or 298 Kelvin, and standard pressure is usually 1 bar, or we can consider it as nearly 1 atmosphere. Now here delta G0 value at various temperatures is plotted. Now the standard value corresponds to that at standard conditions, and here the temperature is changing, so we cannot say this is a plot of standard free energy change, but free energy change with the temperature. Now in the ligand diagram, at 1600 degrees Celsius, delta G for the reaction 2C plus O2 giving 2CO2 is 500 kilojoules per mole, and for the reaction 2Fe plus O2 giving 2FeO is minus 200 kilojoules per mole. If you reverse this equation, we get 2FeO giving 2Fe plus O2 delta G is equal to plus 200 kilojoules per mole. Now if you add 1 and 3, then we get 2C plus 2FeO giving 2Fe plus CO2, and corresponding free energy change is minus 300 kilojoules per mole. Now this minus sign indicates that the reaction is spontaneous. So a ligand diagram uses the spontaneity of a redox reaction. Now there are limitations to these interpretations from ligand diagram. One is that equilibrium cannot be attained in a reaction involving the reduction of the ore to the metal, because in most cases these reactions are conducted in a furnace, and the reactants and sometimes the products may also be in the solid state, so there is no sufficient time to get into contact between the reactant and products. So equilibrium cannot be attained during the reaction in a furnace, because in most reactions the reactants and the solids are in the solid state. Only in a solution state there is sufficient contact between the reactant molecules and product molecules to attain equilibrium. And again, the time of contact between the reactants and products is less in a blast furnace or in a furnace where the actual reduction process takes place. So these are the drawbacks of interpretation from a ligand diagram. Now extraction of iron from its oxide ore. The most important ore of iron is hematite. Now this may be subjected to concentration and then calcination and roasting. Now Fe2O3 is formed. Now that is reduced in a blast furnace. Now before proceeding to the reduction, the impurity present in an ore, usually it is taken from the earth. So silicon dioxide is a probable impurity in an ore. Now silicon dioxide is an acidic oxide. So this may be the main gauge. Now another compound, it is acidic oxide, so a basic compound, that is calcium oxide, is added. Now this added compound is called flax, and we get a low melting compound, ionic compound, a low melting ionic compound, here calcium silicate, and this is known as slag. So this is a general equation. Ganj plus flax gives slag. Ganj plus flax gives slag. Now in this manner, most of the ganj may be removed during extraction of the metal. Now calcium oxide may be obtained from calcium carbonate, a natural compound. So to avoid high cost for production of metal, we use this natural compound calcium carbonate known as limestone, which can decompose to give calcium oxide and carbon dioxide. Now this calcium oxide can act as flux, and again calcium oxide is a basic compound. So if ganj is acidic, then the flux used will be basic, and in some cases the ganj can be basic and then the flux used is acidic. So for example, if the ganj is calcium oxide or limestone, then we add silicon dioxide as the flux. Now extraction of iron is done in a large furnace called blast furnace. A furnace called blast furnace, which is a long tunnel-like apparatus provided with a bottom supply of air, hot air blast, it is said. And then the substances which are added to the furnace at the top is called charge, CHARG, charge. And here the charge consists of the ore, oxide ore, then the flux, that is limestone, and the reducing agent, that is coke, which is a form of carbon. Now there is what is known as a cup and cone arrangement. When this cup is filled with the charge, due to the weight of the charge, the cone moves down, and then there is a uniform supply of the ore plus flux plus coke, that is charge, into the furnace. Now the furnace will be maintained at different temperature zones or regions. At each temperature zone, a particular chemical reaction or a set of chemical reactions occur predominantly. Now far down the furnace, that is in this region where there is air blast, hot air blast, and the temperature is maintained near about 2170 Kelvin, the coke in the charge is oxidized to by this air blast, which contain oxygen also. So coke, that is carbon, is oxidized to carbon dioxide, and this gas rises up through the furnace. Now there some Fe2O3 is FeO, ferrous oxide, is reduced by coke to Fe, and carbon monoxide, which also moves up. Now the rising carbon dioxide is reduced by coke in the upper region, because there is a continuous supply of charge, that is ore plus flux plus carbon, so there is a continuous supply, so that the rising carbon dioxide is reduced by coke in the upper region, having a temperature range of 900 to 1500 Kelvin, which is lower than the temperature in the lower part of the furnace. So as we rise from the lower part to the higher part, the temperature range decreases, or the temperature decreases, the temperature of the zone decreases. So in the upper part, carbon dioxide rising will combine with the carbon, producing carbon monoxide, and carbon monoxide will reduce ferrous oxide in that region to iron and carbon dioxide. Now at the topmost part of the furnace, the limestone, the temperature is kept at the range of 500 to 800 Kelvin, and limestone, which is calcium carbonate, which is the flux added to the charge, decomposes, giving calcium oxide and carbon dioxide will escape through the opening at the top. Now this calcium oxide combines with the ganj and form with the silicon dioxide and forms calcium silicate, which is a low melting substance called slag, and the slag moves down, and there is a particular region in the furnace where the temperature range is 500 to 800 Kelvin. There Fe2O3 is reduced by carbon monoxide to Fe3O4. Actually, it is partial reduction of Fe2O3 to FeO. Now that FeO combines with Fe2O3 to produce Fe3O4. So that's a reduction process. Conversion of Fe2O3 to Fe3O4 is a reduction process by carbon monoxide, and then carbon monoxide is getting oxidized to carbon dioxide. Now Fe3O4 is reduced by carbon monoxide to FeO and carbon dioxide. Now this FeO is reduced to Fe in the region maintained at a temperature range of 900 to 1500 Kelvin, FeO reduced to Fe by carbon monoxide. So this process occurs in various temperature zones. Now iron is formed in the form of sponge in the low temperature region. When it moves down, it melts. Now in metals, the bonding is somewhat covalent in nature. The particular type of bonding is called metallic bonding, which is something approximately equal to covalent bonding. Now in the lowermost part of the furnace, blast furnace, the metal will form in a liquid. It will melt to a liquid. The spongy metal formed, metal formed will come down, and at the high temperature region it will melt. And since the bonding is something covalent, and then the slag will also melt to a liquid. Since slag is here calcium silicate, and the metal is iron, which is having a covalent type bonding, and since this metal is having a high density and calcium silicate is having ionic bonding, now these two type of bonding features will make these two liquids immiscible, just like water and oil. In oil, the bonding is covalent in character. In water, the bonding is polar in character, and so water is immiscible with oil. Similarly, the molten metal is immiscible with molten slag, because the bonding feature in these two are different. So we will get a bottom layer of molten metal and an upper layer of molten slag, and now these two are immiscible, and we can isolate the molten metal from the upper layer as liquid, and the liquid iron formed there is called pig iron, which can be solidified. Now molten slag also may be separated. Now then the metal after solidification is called pig iron, which will contain various impurities. Now we'll study about the nature of pig iron later. Thanks for listening me.